Good morning, everyone, and good afternoon, everyone who is joining online from IST time. Welcome to my proposal presentation. Uh, my thesis is titled Neurosymbolic Multi-Agent AI for uh, Robust, Intelligent, and Trustworthy Industrial Systems. And huge thanks to my dissertation committee, Dr. Amit Chet, who is my advisor, Dr. Marco Waiprota, the examination chair, Dr. Vignesh Narayan, assistant professor at USC, and Dr. Corey Henson from Bosch AI Center, Pittsburgh, and Dr. Dawal Patel from IBM Research. And so let me start with giving a motivating example. So as shown in this figure, the industrial systems, for example, the manufacturing systems, they are highly interconnected. They have sensors generating continuous streams of data and robots that execute complex operations and control systems coordinating workflows. So all of this creates a highly interconnected and dynamic data-rich environment. Importantly, these are high-stakes environment, means even small errors in production or decision-making can lead to costly downtime and safety risk. Because of this, the decision-making in industrial systems remains fundamentally challenging. The reasons this problem is challenging are the rare events, which are extremely rare, often less than 1%, and the data is highly multimodal, contains data types, time series, images, and text, and the systems are non-stationary, means the aging equipments and the configuration changes can lead to the shift of statistical properties of the data that is generated over time. And the operations are constrained by safety, latency, and logic. Current AI systems are not designed for this setting. They struggle under data imbalance and drift. By drift here, I mean the patterns in the data are changing over time, and they provide correlation without causal ground. They focus on isolated prediction tasks. Because of that, they operate as disconnected pipelines. So the key issue here is we have some component, but not true industrial intelligence. By industrial intelligence here means the ability of industrial systems to perceive, reason, predict, and act using data, AI, and domain knowledge to optimize the operations and the reliability. So industrial intelligence remains fragmented, brittle, and difficult to trust. So recent studies have shown that the operational complexity in manufacturing is increasing rapidly, and but the AI adoption is still limited by the integration and the scalability challenges. So there is a clear gap. The complexity in the industrial systems is increasing faster than the industrial AI's ability to reason about it. And importantly, the industrial intelligence requires more than just prediction. Current industrial challenges show that the isolated predictors are not enough. We need systems that are robust, integrated, and explainable. To formulate this, we need to rethink what industrial AI should be. In order to address this, I defined three key properties in my dissertation. Robustness. The systems should have ability to maintain correct, stable behavior under real industrial stresses like extreme class imbalance, noise, drift, and change in configurations. Secondly, intelligence. The systems should have the ability to reason, plan, coordinate, generalize across context, and perform causal and counterfactual inference using symbolic abstractions and learned models. Thirdly, trustworthiness. The system outputs should be able to audited, explain, and align to operator goals and domain rules. So industrial AI must move from isolated models to systems that learn from rare event data, predict under uncertainty, reason with knowledge and causality, collaborate across tasks, and operate in real-world environments. Then moving to the core paradigm of my research, first, the neurosymbolic AI combines data-driven learning from neural models with symbolic knowledge from ontologies, rules, and knowledge graphs. This allows a system to move beyond correlation-based prediction towards knowledge-grounded inference and that enables reasoning and explainability. Now, in industrial settings, decision-making is not a single task. It involves multiple interdependent tasks like anomaly detection, forecasting, causal discovery, root cause analysis, and domain-specific question answering. And a single model cannot handle all these tasks reliably. This led to multi-agent copilots, where each agent specializes in a task and they coordinate through adaptive orchestration with human-in-the-loop collaboration. When we combine these two ideas, we get neurosymbolic multi-agent AI. This enables shared world models across agents, knowledge-grounded reasoning, robust learning, and coordinated and trustworthy decision support. Then this leads to my thesis statements. Industrial decision making requires reasoning under uncertainty by integrating heterogeneous data, domain constraints, and causal relationships. This thesis argues that neurosymbolic multi-agent AI provides a unified framework that combines data-driven learning, symbolic process knowledge, and causal reasoning to enable robust, intelligent, and operationally trustworthy decision-making in industrial environments. To operationalize this, I structure my work across 5 research questions. RQ1, how to learn from rare event data. RQ2, which models are reliable under industrial constraints. And RQ3, how to enable trustworthy reasoning through inference. And RQ4, how to enable how to build coordinated multi-agent systems. And finally, RQ5, how do we deploy these systems in real environments? So these research questions correspond to 5 contribution areas. Firstly, C1, data foundations. C2, specialized models. C3, neurosymbolic reasoning. C4, multi-agent architectures. And C5, operational deployment. So the contributions from C1 to C4 will be covered in this presentation. And these are my foundational work that has been published. And first, moving on to the first research question, how can rare event industrial database systems be characterized and enriched to enable robust learning? So this relates to the first contribution, which is characterization. So in this contribution, characterization means I am basically dealing with the problem of rare event learning because it was fundamentally a challenging problem in the manufacturing domain. And so here I am basically worked on characterize the data related to rare event learning. So in industrial systems, the failures are extremely rare. They occur less than 1% of the time, but they cause high downtime and cost. The standard models struggle because of few reasons like skewed trust distribution, noise, high dimensionality, and uncertainty and bias. And by the time we were started to look at this problem, there was no unified taxonomy and compiled list of studies of rare event learning. So the contribution of the goal 1 was to characterize, organize, and improve industrial rare event data so that downstream models and the multi-agent systems and copilot architectures can learn robustly despite imbalance, noise, and drift-like conditions. So in this work, we came up with 4 key dimensions in rare event learning. They are data processing approaches, algorithmic approaches, and evaluation approaches. And in this work, we identified why the events are rare. So they can be rare because of the reasons like narrow labels, low frequency, subjective curated decisions, sampling bias, and the cost and measurement errors that can happen during data curation. And this all creates data imbalance and complexity. And in this research, we have introduced a conceptual contribution of rarity hierarchy to compare the studies more systematically. So it ranges from extremely rare conditions to frequently rare conditions as shown in this figure. And also we identified different rare event data types like naturally rare, derived and simulated or synthetic data sets. And also we did a thorough comparison of the algorithmic techniques that has been used in the event learning. For that, we identified 5 major algorithmic groupings, and like we compared it using 4 major factors as shown in this table. And we realized that no single method satisfied all the requirements that we catered, for example, like efficiency, interpretability, performance, and the data availability. And we realized that the advanced models like Markov chains or active learning methods, they achieved high performance, but they lack interpretability and trust. And all of these approaches are highly data dependent and not generalizable. And importantly, none of these methods explicitly model causality or reasoning. And we concluded that the rare event learning is fundamentally a trade-off problem, and it's not a model selection problem. And then moving to the second sub contribution of this major first contribution, it was developing data enrichment pipelines for rare event learning. So this includes techniques like data augmentation, sampling, and imputation. So here in this slide, I have included the methods that we have tested and analyzed for our datasets. So we have used 5 real-world manufacturing-based datasets, and the goal of this study was to improve the data quality, class imbalance, class balance, and the representation of rare events.
Just missing this is that the out of the call and then ask if you could allow them back in.
I didn't get any request to accept.
Maybe this is.
If you can send the link.
Who is not on the call now?
Dr. Sheth.
Dr. Chat. Oh no, that's important.
Maybe I can continue.
Yeah, I think you should. Are you sending the link?
Yes, so
No, what happened?
this is the data enrichment pipeline that we have designed and evaluated on our datasets. So as key findings, we realized that the feature-based time series augmentation methods improved rare event prediction by 41% of F1 scores, and the combination of augmentation and sampling methods performed better than either alone, and the resampling improved the time series signal quality. For example, in one dataset, we increased the point from 0.7 to 0.9. And why this study mattered in my research is, so these pipelines, they form the robust data layer required for my next subsequent contributions. And these methods were able to stabilize the event learning problem, especially in the extremely rare and very rare datasets, which I have set up in my hierarchy. And then, yeah, that was the main conclusions. So the conclusions of the first research question was to design taxonomies and enrichment pipelines that enhance the data coverage, reduce imbalance, and improve the interpretability of the rare event learning problem. And then secondly, moving to the specialization, which is the outcome of my second research question, which models remain reliably under rarity and non-stationarity. So in industrial systems, failures are both rare and they are observed as anomalies in sensors and visual data. So from this section onwards, I am focusing more on anomaly detection and prediction. So here, the detection means identifying an anomaly after the event occurs, and prediction means identifying the anomalies before the event actually occurs. So here, I have 3 research questions to evaluate how efficient are unimodal approaches, how efficient multimodal approaches, and how can we leverage time series foundational models in anomaly detection and prediction. So then first, moving to the first sub question, how can we use unimodal approaches in identifying anomalies? So here we mainly take the problem in identifying them in assembly pipelines. So animal prediction in assembly pipelines is a hard problem due to few reasons. Firstly, the anomalies are extremely rare. The SOTA models could achieve only around 50% in prediction and 66 for detection. And secondly, we are dealing with high dimensional data. And thirdly, we lack high fidelity simulation data. And also there is a major interpretability gap. And finally, the current methods, they treat anomalies as isolated events. They don't answer when an anomaly will occur and which components will fail and how the failures interact throughout the system. So to address this, we propose this RI2AP system, which is a robust and interpretable 2D anomaly prediction framework. Here, the developed model predicted two things. First, the next step sensor values, which captures how the system evolves over time. And secondly, the anomaly severity token, which encodes how abnormal the system is. And in this research, so in order to combine prediction, instead of using simple simple aggregation method, we use causal combining rules like NeSy OR and NeSy max. And the system is deployed in future factories assembly set, which I am explaining in the next slide, and it provided 30% improvement in F1 point. So this is the first use case, which is the rocket assembly pipeline at future factories. This pipeline is implemented in the McNair Aerospace Center at University of South Carolina. So what they are working on is, so in their pipeline, they have 4 robots. So they are working on assembling a rocket as shown in this figure. So they have 4 different rocket parts. So the robots are working on assembling each part at separate cycle states that has been defined in their pipeline. And so this pipeline consists of 21 different cell cycle states, and this produces multimodal data in respect to this assembly process. So then moving into the second sub task of this unimodal approaches, it is image-based anomaly detection in assembly pipelines. So the problem is fundamentally a challenging problem because of few reasons. Firstly, the visual differences between the normal and the loud images are extremely subtle. As shown in this figure, you can see that there is no that visual difference between the normal and the abnormal images, and structural similarity was around 0.9. So the model struggled to discriminate. Secondly, the data is highly imbalanced. And thirdly, the models tend to focus on irrelevant features instead of the actual object. So as shown in the scope and visualization, the attention is often placed outside the assembly components. And fourthly, there are generalization issues. And finally, there are interpretability issues. So to solve this, we introduced this assembly AI pipeline, which is an interpretable image-based anomaly detection pipeline. And to address, so in this AI pipeline, it introduced a new image dataset, which is derived from the future factories multimodal dataset, and it provided a region of interest and bounding boxes for anomaly relevant regions. And here we implemented a robust anomaly detection model, which is a fine-tuned efficient net model, and it achieved almost like 96% accuracy in the future factories dataset. And also it provided interpretability at 2 levels. At the user level, we designed and developed a process ontology to validate predictions obtained by the SMI model. And at the model level, the score cam visualization highlighted the actual failure regions, and it ensures that the model focused more on the correct components rather than the background. And the system is deployed in the future factories assembly set as well. In my 5th contribution, I will explain more details on the deployment. And Then second, moving on to the multimodal anomaly detection work. So the unimodal approaches, they fail in manufacturing as they miss critical dependencies across the modalities. For example, the time series alone cannot capture visual context and the image models ignore temporal behavior. At the same time, the multimodal datasets are extremely scarce and the existing fusion methods, they use context. Means they ignore semantic relationships and they create inconsistencies across modalities. To address this, we proposed the NSF map framework, which is a neurosymbolic multi-agent multi-model framework that jointly models images, time series, and process knowledge. And this is also deployed in the feature factory cell, and it was able to perform robustly under RAD conditions. And the architecture of NSF map integrated three components. Firstly, the visual features are extracted using efficient net, and template patterns are modeled using a time series autoencoder. And then the decision level fusion, which is a mechanism of combining two classifiers, it is performed to combine modality specific predictions. And this method was able to achieve 18% of improvement in the F1 scores. And secondly, we freeze the encoder of the time series autoencoder. By then, we achieved 23% of improvement. And thirdly, we introduced a knowledge infusion layer that injects sensor constraints and process ontology to enforce the learning process. And it achieved 29% of improvement in accuracy and F1 scores. And these are some of the results we have got. And then thirdly, moving to the third sub contribution of this second RQ. So it was to evaluate how time series foundational models perform in anomaly detection and prediction. So to answer this, we performed the first systematic evaluation of time series foundation models across 5 industrial datasets. And and here we used 5 different time series foundation models. So these are the statistics of the reference time series foundation models that we have used. And then we evaluated them in 3 steps. Firstly, zero shot usage using the built-in forecasting or detection capabilities in them. Secondly, fine-tuning on each of the datasets that we have used. And thirdly, benchmarking them against traditional models like XGBoost and autoencoders. And so the results showed a clear pattern. While the time series foundation models like Time GPT, Time MOE, and Cronus performed well for forecasting, they struggled for anomaly detection, and fine-tuning provided only marginal improvements, and the traditional models like XGBoost and weighted XGBoost, they constantly outperformed across all the datasets, and time series foundation models are computationally expensive, up to 10 to 15 times slower than the baselines. And the key takeaway was that the TSFMs are not designed for anomaly detection. They are black box inefficient and they fail to handle rare or pattern-free signals. And so industrial settings, the lightweight task-specific models remain more robust, interpretable, and practical. And this was the conclusion we came up in 2024 December. So the RQ2 contributions were developing lightweight, explainable anomaly and forecasting models that outperformed heavy time series foundational models in real industrial data. And then thirdly, moving to the inference, which is the contribution of my third research question. The question is, how can neurosymbolic integration of process knowledge and causal reasoning improve trustworthy inference, reasoning, and explainability in industrial systems? The manufacturing processes, as I explained earlier, they are inherently complex and they involve multiple components, temporal steps, process logs, and humans, and also many interdependencies. So in practice, this knowledge is scattered across manuals, process specifications, and within experts, and they are not explicitly modeled. So we address this by modeling the manufacturing process as a dynamic multimodal process knowledge graph. So it integrates all these components along with multimodal data such as images, time series, or process logs. And so this created a semantically grounded representation for my configurations. So this motivated us to use neurosymbolic AI for anomaly prediction. So the pure neural models, they learn correlations, but they lack process understanding. So they failed under data scarcity and and constraint violations. In manufacturing, the anomalies are usually governed by process rules. For example, some of the anomalies are impossible in certain cycle states. So without this knowledge, the models cannot distinguish valid and invalid anomalies. To address this in the NSF map work, which I explained earlier, we integrated the symbolic process knowledge with neural models. So in this work, we injected constraints like sensor ranges and cycle state logic, and they enforced consistency, and we could generate explanations which are grounded in process semantics. And then we extend this idea of knowledge infusion to demand forecasting in manufacturing. I would say around like 50 rules.
Okay. And did you have any issue with consistency among rules?
Yeah, so for example, in those rules, it includes a process sequence. For example, there are 21 cycle states, and so there were anomalies that happen in several states. So that cannot happen in the other states. So these were some of the consistency issues that we have found and mitigated through the process ontology.
Okay.
Yeah, so in the demand forecasting work, so in real production settings, the forecasting is a challenging issue because the data is non-stationary and they are constrained by process conditions. So to address the problem of this demand forecasting, we incorporated domain knowledge directly into the learning process. So we perform a feature infusion where the additional context like the process states and sensor constraints and the domain variables, they are directly integrated into the model. So this enabled knowledge guided forecasting where the predictions are aligned with real world operational rules rather than purely data driven patterns. So we implement this using the LSTM model as you see in this figure, and it is augmented with additional knowledge as informed features. So this is the use case where this demand forecasting has been verified on. So it is the Vegemite production use case where we got the data from Swinburne University, Australia. And so here, this is the pipeline of the Vegemite yeast evaporation process, and they generate time series data for this pipeline. And so for the target data variables, we had the the weight of the three types of yeast which they are working on evaporating. And for the contextual or the domain infused columns, we have 9 process variables that are defined by the domain experts. And this method that we have incorporated, it was able to perform well and improve the production accuracy as shown in these tables. And then moving on to the third category, where we use neurosymbolic AI in causal diagnosis. So purely the data-driven causal discovery, it was not enough in industrial settings due to several reasons. Firstly, under noisy and rare conditions, the data-driven methods can learn spurious or uh, temporarily invalid relationships. So the causal graphs itself become unreliable. And secondly, in the industrial systems, they are constrained. This means they follow actuator sensor relationships and stage-wise process rules. So the standard causal discovery methods can ignore this structure. And because of this, the wrong edges can lead to incorrect root cause decisions, which can lead to cost or unsafe conditions. So by using symbolic methods, we were able to achieve explainability, where the every edge in the causal graph could be traced and justified using the knowledge graph and the process ontology, and the domain knowledge infusion, where we were able to constrain the search space using process knowledge, and graph refinement, where we can add or remove the edges based on domain knowledge. So on the right, you see our system. So it builds and interactively refines the causal graphs using ontology level knowledge, and it makes the causal graphs both valid and also trustworthy. So here you see the node description. So they were directly obtained from the dynamic process ontology and the knowledge graph that we have designed and developed. And then moving on to the third use case where my research has been validated on. So it is planar sensor element grinding process at Bosch. Here simply there is a video that I can show. So simply there are two robots who are working on grinding a metallic rod named as planar sensor element. So here you saw the two robots, they are coordinatively grinding this planar sensor element, and there is a sequence of grinding steps that is happening in this pipeline. For example, the arm one grinds some of the places, and the arm two grinds some of the places defined in the planar sensor element. And by the domains experts, we were able to come up with certain rules, some kind of process rules that are defined for this pipeline. For example, as shown in this figure 3, we define rules like the control parameters. For example, the set angle and the grinding depth that are specified in the robots, they directly occur the observation parameters. For example, the depth of the place which is being grounded by the robot. And so this is an example of what are the this is a representation of what are the forbidden rules and what are the allowed rules in this PSE use case. And then moving to a real causal agent, which we have designed and developed. It is named as causal trace. It is a neurosymbolic causal analytic agent designed for smart manufacturing. So in this system, the users can directly upload time series data, and then it does causal discovery and root cause analysis. And it's a chatbot kind of a system where the users were able to answer questions related to causal graph structure, causal reasoning, and root cause analysis. And then in the causal trace agent, we use several neural methods like causal discovery, total causal effect estimation, and root cause analysis. And for the symbolic method, we use dynamic process ontology, smart manufacturing knowledge graphs, and causal graph prompt injection. And these are the snapshots of the KG and the process ontology that we have. And then these are some of the risk evaluation results. So in the causal trace, the users were able to change the value of one sensor variable and see how it will affect the other sensor variable. And it also generated explanations, all based on statistical evaluations that we conducted. And we have several baselines that we developed. Firstly, the Pearson correlation-based root cause analysis baseline, and the causal trace variant without the KG and ontology. And compared to them, the full causal trace achieved a high performance in the metrics that are defined in this table. And so the contributions in the RQ3 was defining methods to proper anomaly detection, prediction, and forecasting and causal discovery, and enhance this with fusing knowledge graphs, ontologies, and domain rules. And then moving to the fourth research question, how can neurosymbolic multi-agent copilots enable adaptive, intelligent, and collaborative decision-making across heterogeneous industrial tasks? So till now, you saw separate tasks are performed by separate systems, but as I said in the beginning, that should not work in the industrial environments. Means in real industry or the factory settings, we need systems that can talk to each other, coordinate their tasks, and perform reliably. So that was the main problem which I have identified, and this RQ4 directly addressed that issue. And so as the contribution, I have defined the concept of neurosymbolic multi-agent copilot, where I am proposing a general architecture for neurosymbolic multi-agent copilots. So the architecture backbone includes three layers as data layer, utility layer, which includes like resources, LLMs, KGs, ontologies, and then the agent layer and the user interface layer. So there can be several agents that perform different tasks in a manufacturing flow, and the agents directly access the user interface, and the users can interact with the UI, and it can provide feedback loops so that the agents improve their task performance. So this neurosymbolic multi-agent backbone is governed by agentic uh, infrastructure and governance principles. For example, there can be agentic design patterns like reflection planning, use, and multi-agent coordination, and design patterns like plan, executor, or react, and design protocols like MCP, A2A, and frameworks like LangGraph, LangChain. And all the things happen in these agentic copilots are saved as memory, which can be long-term, short-term, or semantic, episodic, or procedural. So then this slide explains how we conceptualize the world modeling concept in the neurosymbolic multi-agent copilots. So here, the knowledge is split into two parts. The shared memory, it includes agent world model, and the local memory, it included the agent task knowledge. So the shared world memory, it's a global layer that stores the domain knowledge. For example, things like machines, sensors, and their relationships and causal dependencies. So all the agents in a system, they read from and write to this shared layer. Uh, and so everyone operates on a constant understanding of the system. And then each agent has its local memory, which contains like task specific information. For example, an anomaly detection agent, it stores detected anomalies. So when the agents operate, so they map their local outputs to the shared world model. So in that case, in the anomaly prediction, the anomaly is not just a number, it gets grounded into specific sensor, time, machine, and possible failure modes. And then moving to the first implementation of neurosymbolic multi-agent copilots, which I have designed and developed, it is Smart Pilot, which is a multi-agent copilot for adaptive and intelligent manufacturing. So it includes multi-agent architecture, and it relies on multimodal data, which I use time series images and text. And importantly, it is based on custom, compact, and neurosymbolic AI model. So what these terms mean are compact means all the agents that I have, they are based on lightweight components, and custom means there are task-specific agents to perform different tasks. And neurosymbolic means I have used the combination of neural and symbolic fusion, which leads to causal and common sense reasoning and provided transparent and context-aware decisions for manufacturing. So the end users that I target for Smart Pilot is manufacturing specialist or anyone who is working related to manufacturing. And then this is the core framework of Smart Pilot, which we have defined. It includes 4 different agents. The predictive, which is the anomaly prediction. So here I have used the same NSF model, NSF map model I have explained, and foresight. So here I have used the same knowledge infused LSTM model I explained in the previous section, and the causal trace. It is the same causal analysis agent, which does cost analysis and causal discovery, and the InfoGuide agent, it's a RAG-based QA agent, which is based on manufacturing specific manuals and provides answers by a RAG-based method that we have designed. And the agents are connected and they are talking with each other, and we used LangChain concept and transfer learning in between the agent interactions, and all the things happening in this pipeline are saved as semantic, episodic, and procedural memory. So by episodic memory, I meant that the logs and the interactions, timestamps interactions in the system, for example, like postal discovery and the RC runs are saved. And by semantic memory means It stores the structured annotations of sensors in the system. And by procedure memory, I meant like things like user preferences, like choosing algorithms or the display settings. And so this is the agent-based architecture of Smart Pilot. So it's a composite system which involves multiple components, interactions, and data types. And so then in this work, we carried out a C3N principle-based evaluation. So C3N here means custom, compact, and composite AI with neurosymbolic methods. So these methods are initially defined in the C3N article that we published last year. It defined 14 key principles that are needed to build enterprise AI mission critical applications. So Smart Pilot is able to achieve 10 of those principles. So for the robustness related principles, the KG, so first consistency, the KG and the ontology, it ensures stable terminology across the agents and the queries we have used. And for reliability, it produced hallucination-free outputs. And then for the intelligent behavior, causality, firstly, the causal agent was able to provide causal relations and counterfactual narratives, and the system was able to provide logically infer conclusions. And then abstraction means the low-level sensor or the image data were abstracted into high-level concepts in the process ontology. And planning, the Smart Pilot used lightweight orchestration for the task routing. And to make the outputs trustworthy, we were able to achieve first grounding, where the outputs are grounded in the symbolic methods, mean the ontology entities and the sensor IDs, and explainability. It achieved explainability using score CAM visualizations, ontology explanations, and causal narratives. And the users were able to inspect model settings, features, and causal graphs. By that, it achieved interpretability and attribution. The users were able to trace the outputs for the predictions and the infer causes and see what features have been used. So in this evaluation, Smart Pilot achieved weighted points of 0.62 between LLM evaluators and 0.58 in human in the loop evaluations. And it achieved strong task-dependent performance. For example, for the RCA, it achieved high metrics as MAP like metrics. And so these are some of the results that we conducted in the C3N evaluation. So you can see agent-wise performance. And so in this study, we defined close to 100 question and answer pairs, and they were validated by domain experts. And then they were again validated by 2 LLMs and 6 human evaluators. And in all of these settings, it performed like very good results. And then moving into the second use case, second implementation, it is the currently ongoing work which I am doing at Bosch. It's causal pulse, which is a industrial level multi-agent copilot for causal diagnostics. So here it included 4 layers. So in the architecture. So in this pipeline, we are mainly dealing with tasks related to causal diagnosis. For example, like data processing, anomaly detection, causal discovery, root cause analysis, recommendation, and process optimization. So the architecture included 4 layers as shown: data layer, utility layer, agent layer, and user-facing layer. So here we have used agentic design principles like agent to A protocols and MCP connections. And in this pipeline, we have 2 types of components: task-specific components, which includes the modules related to causal diagnostics, and the common components, which includes the components that can be shared and coordinated with other use cases and other copilot systems. So it was quite modular system. And then moving on to the third implementation of neurosymbolic multi-agent copilot. So that related to AssetOps Bench, which is a product of IBM. So it is a multi-agent system that has 4 different agents: failure mode and sensor relation agent, time series foundational model agent, work order agent, and IoT agent. So here, my contribution was to develop a evaluation pipeline for this. So here we conducted a community-wide competition for this evaluation, which includes nearly 300 participants, and it was conducted across 3 months. And then the RQ4 contribution so far is developing and evaluating multi-agent architectures which enabled autonomous agent collaboration. Then moving to the fifth research question, how can neurosymbolic multi-agent copilots be operationalized in real environment settings? So here I am answering 2 research questions. How can we use embodied question answering to enable decision support, and how the neurosymbolic multi-agent copilots be deployed across several architectures? Firstly, moving to the first task, embodied operational industry 4.0. So this is an ongoing work which we are currently doing. So the gap we have identified in current LLM-based QA systems is they fail in mission critical applications and they provide generic answers. And also one limitation that we have found in systems like Smart Pilot is it provides correct answers, but there were no verifiable provenance in. For example, if we talk about time series data, and if we ask about an anomaly, it just provided if there is an anomaly and root cause for that. But we could not verify the exact location where the anomaly happened and what exact features and how the change of the statistical properties led to the final answer. And also, the counterfactuals with Smart Pilot generated, they were not testable, means there were no model in behind that that could answer probabilistically how the counterfactuals are correct. And so we define this as operational intelligence problem. By operational intelligence, I meant the ability of a system to use real-time data, knowledge, and reasoning to support actionable decisions. And from this problem, we define industrial maintenance QA as the embodied decision problem. By embodied here means that the system is grounded in real-world sense data and time, and it operates as a perception, reasoning, prediction, decision loop to support actionable decisions. So to make this thing work, we have defined this industrial asset EQA system, which includes episodic memory, failure mode and effect analysis, knowledge graph, risk and counterfactual simulator, and verify and safety gate. And then moving to the second contribution of this main contribution. So it is development of the deployment of the neurosymbolic multi-agent copilot. So here is a deployment pipeline that I have currently identified, and it includes 3 stages. So these copilots can be first virtually deployed as a prototype using services like testbed as a service, and then we can move to the real deployment. For example, in the future factories that where we are currently working on initial experiments related to real world deployment, and then thirdly we can go to the public hosting mechanisms, which include like MQTT broker kind of setup. And then the proposing RQ5 contributions will be designing and development of embodied operational intelligence frameworks, deployment setups, and optimization techniques for neurosymbolic multi-agent copilots. And then these are my plan from proposal to dissertation. So currently I have completed RQ1 and RQ1, 2, 3, and 3. And then currently I'm working on RQ4 and RQ5. And so the key takeaways till now, which I have identified, is that industrial AI can be enhanced so that it can learn robustly, reason with domain grounding, collaborate through neurosymbolic multi-agent architectures, and they can be operationalized as neurosymbolic multi-agent copilots in real factory environments. And so this is my timeline for the rest of the RQ4 and 5. So from March 2026 to November, I will work on implementing and evaluating the causal pulse system and design, deploy, implement, and evaluate the embodied operational intelligence framework and design deployment strategies for neurosymbolic copilots and work on dissertation writing. And November, I'm hoping to do my defense. And these are some of the impact of my work. So in my PhD, I was able to collaborate with multiple industrial institutions and research labs like Bosch, IBM, Next Future Factory, and Swinburne and Clemson Composites Center. And then I was able to do 2 labs and 1 data challenge with IBM and 2 tutorials with Bosch and 2 industry internships, 1 in Bosch and 1 in IBM. And I got the opportunity to mentor students, and all of my research, they were like had good outcome, and for example, like best paper and best poster awards and multiple. I was able to collaborate with many of my seniors, and I had many mentors, and I got guidance from multiple people, and I'm even here, like a lot of colleagues collaborated with me, and I appreciate their support, and I'm grateful to them. And thank you.
Thank you. Very nice, full presentation. I guess you really packed it in. You were also, you're also a fast talker, and the material. I mean, I hope everybody agrees that the visuals were impressive. Very well organized. Now we have questions from everybody. I don't know if we should start from the audience, either in the room or online. I see 7 audience members, including the photographer here. So do you have any comments, questions, concerns, people ask or comment? Maybe I realize I'm a little bit out of bounds here, but I do recognize most of you, in fact, all of you. Do you collaborate on some of this work? Yes. Okay. Very good. So this work is part of the lab activity, you know. Okay, that's a good check, you know, to find out. General questions. I'm going to start and ask you a little something. So this is a fairly detailed question. When if you could go please to slide 50. You mentioned a number of measures of quality at the bottom of the slide. And I checked, I made a search for RCA and kappa in your dissertation, and I didn't find them. RCA was only found in a caption, okay? But a kappa was not found at all, at least I couldn't find it by search. In any case, the definitions are in there. And I wonder whether you could briefly tell me what those measures are. This is more a question of examination than proposal question. Yes.
Yeah. So here, Cohen's kappa score. So it is a measure that we use to evaluate the inter-annotator agreement. So here, to evaluate this system, so we use LLM-based evaluation and human-in-the-loop evaluation. So we had 2 LLMs, one GPT for Omni and one Llama. So we evaluated like how the response of one LLM can be compared with the responses of the other LLM. So in this figure, for example, the responses of LLM1 match to LLM2 in 0.62%. So the scale is from -1 to +1 here. So it was agreed up to 0.62. So this is the Cohen kappa score of that. And also we had 6 human evaluators. So all of this, so for example, the response of the second human evaluator matched with the third in 0.46.
So kappa summarizes this table in a single number. Is that what you would say, or is it just representing one entry in the table?
One entry in the table.
One entry in the table. Okay. And what is RCA?
RCA is root cause analysis.
Okay, can you go back to that? Okay. So, oh, I see. So for the root cause analysis, you give a number of measures. Can you describe all four of them? MAP, MRR, and JACAR. Can you please tell me what they are?
Yeah. So the simplest one here is Jacquard Similarity Index. So to evaluate this RCA performance, so we had two things. One, the response from the smart pilot system itself, and one, the domain experts, how they define the root causes for several anomalies. So for this Jacquard index, it just measured the similarity, how similar these two terms are. And so for the other things, mean average precision, precision recall, and mean reciprocal. Something I can't remember that. So there we had a rank. For example, at 3. So for example, for one anomaly, we had like rank list of root causes. For example, for an nose-cone anomaly, there can be 3 root causes, 3 sensors occurring. So here we tested the rank also. So we identified that comparing all the 3 ranks in the sensor list, we were able to achieve the correct sensor order, which affected the anomalies.
Thank you. That's good. Questions from anybody still? Dr. Ayan, you're in the room, so I'm picking on you. Do you have any questions like this now? Yeah, question.
Chathurangi, go to RQ4.
Yeah, I'm in RQ.
Yeah. So go down. Not this one. No. So will you this? Yeah, this is fine. Would you in our group we're working on orchestration, and kind of we have already talked about the idea of composite AI. So how do you think that that is relevant here, that you can leverage here?
You mean composite AI? I did not understand. I did not the
composite AI in C3N. We have the title is composite AI, right? So we have you say that to do a complete comprehensive application, AI based application, you might need a variety of um, agents, and here there is one based on LSTM, another based on something else, RAG, something else like InfoGuide is a very different kind of agent implemented in a very different way. So can you think of presenting all of these different components as part of, look, this is my composite AI system?
Yeah, of course. So in this system, it is itself a composite system, by means it has like several components as you mentioned. So what is the important thing here is that they work collaboratively. For example, here when the predictive agent gives the anomaly output, it calls the causal trace agent to see the root causes. So then the root cause analysis, that algorithm, that module is activated. So there are like multiple components here talking to each other. So that is what composite AI here I.
Right. What I'm suggesting is that we put it in that vocabulary.
Okay, so do we have questions from the external committee members? So Dr. Hansen, Dr. Patel, do you have any questions for the candidate? If not, I have more.
No, I will ask one questions like which should be kind of fairly kind of go in the same direction at like Prof. Amit kind of mentioned is like when you mentioned this composite AI, right? I recall like there is a popular terminology we are using like compound AI, where like agents of different skill, right, are kind of collaborating in order to solve the kind of problem. So that was the one observation I had, that we should kind of make sure that not introduce any new terms which probably can conflict with the existing literature of body. The second thing is a multi-model, right? So a lot of times I noticed that you wanted to work on the data set which are of different modality, right? But that particular term was not being mentioned, right? So we should kind of, also consider, right? Because the work that you are doing is basically there are data set, and instead of going on a, multi-model, probably you are kind of doing this integration at agentic level, right? So these are kind of, two questions, and I wanted to see your thought, like what's your thought about these two questions? How are you going to align with the terminology? And the second question is that there is a broader interest in a multi-model, so how these kind of work align with multi-model aspect also? Yeah, these are the two questions.
Yeah, so in my work, actually, I have worked on like how we can integrate the two modalities. For example, like time series and images. So we use this fusion method to integrate the two classifiers which work on time series and images. So that is one way that we have used. Uh, yeah, so there can be like some other methods also that we found. So the method that we have used is decision level fusion. So there can be other methods like layered fusion as well, which we found in the literature. And yeah, in terms of integration, there need to be like considerations that we need to take since when we combine like time series images and text, like we should not like sometimes it led to like we could not capture all the signals, and it can lead to like misleading conclusions. So we have to be very careful in using or like fusion techniques that we are using, and the integration patterns that can be used. So yeah, all of this has to be taken care of when they are used in an integrated and a compound system.
All right. Dr. Hanson, you have questions too?
Yeah, actually keep on this slide. So you claim that your approach integrates various like heterogeneous tasks, right? So like you have anomaly detection, forecasting, causal analysis, right? Within this neurosymbolic multi-agent framework. So I'm curious about the role of knowledge within the overall framework. So I mean, I see you in this image, you have like, process ontologies, structural knowledge sources. So if we stick to a particular domain like manufacturing, right, there's a lot of domain knowledge around manufacturing, which I assume is useful in these tasks like anomaly detection, forecasting, causal analysis. So is this domain knowledge is the same domain knowledge being used by these multiple agents? So that would be the first question. Like, is there just a generic domain knowledge available? And then if so, how is it being shared and used by the various agents within this architecture?
Yeah, that's a good question. So, in my third research question, I explained how we used neurosymbolic AI concept in animal prediction, forecasting, and causal discovery. I can take the answers from there. So, in anomaly prediction, we use this dynamic process ontology. And so here, for example, the DPO, the dynamic process in ontology included the sensor ranges, the high and the mean thresholds. So the ranges values, so they were directly infused into the learning process. So when the deep learning model is running, it consistently check if the current sensor value aligns with the threshold limit. So that threshold is itself taken from the Neo4j based. It is queried from the Neo4j based ontology. So that is one way we use knowledge infusion. Means the how we use knowledge. And in another example, so once the predictions are obtained by the predictive agent, so we check it against the ontology that gives us user level explanation. So for example, we checked that if that anomaly can actually be happened in this cycle state. Because there are some anomalies that cannot happen in certain cycle states. So those knowledge are itself in the process ontology. So we compare with those things, and if the prediction is wrong, then we discard the predictions and consider it as the incorrect prediction. So that is another way in how we incorporated knowledge in the predictive agent. And in the foresight agent, so in the Vegemite production use case, which I mentioned, the expert gave us like process parameters that we can use. So they can't be used directly in the learning process, data-driven learning. So in the final layer of the LSTM, like before the classification head, we infused those additional extra 9 features. They were also weight of the raw yeast, but not the initial weight. The weight of the yeast in somewhere in the middle between the process. So that was the knowledge that we have used. And in the causal discovery, so there are manufacturing processes are itself sequence-based processes. For example, the assembly pipeline, there are sequential order of parts which are being assembled, and there is an order of the cycle states. So that information we used in the causal discovery. For example, it had like forbidden edges that we can derive, and also that there are edges that actually need to be included in the causal discovery. So that is the knowledge that we have used. So the knowledge itself used in the causal discovery process, not before or after. So that gave us knowledge guided causal discovery.
Okay, so like that's pretty comprehensive on. Sorry. So that's pretty comprehensive on, how knowledge is being used within each of the individual agents. I'm kind of interested in what knowledge is used across agents. Like, is there shared knowledge that more than one agent is using at any given time? So it needs to be maintained somehow external to any particular agent, because it sounds like each agent has its own knowledge base that it uses for the task, but there's not really much need for sharing across agents. So I'm just curious your thoughts on that.
Yeah. So that concept actually, we are using that concept here, like which we are currently working on the causal pulse agent, where there is shared agent word knowledge, and the agents have their own separate task knowledge. And when they want the world knowledge, they can access the global memory. And when they want only minimum task specific knowledge, then they can access the local memory.
So this is, if I may jump in a moment, Dr. Hanson, apologies. This is work in progress, and it's something that you plan to investigate before you defend your dissertation. This is part of RQ4, and you pointed out RQ4, RQ5 are still in progress. So this is actually going to be described further in your
so
final work.
Conceptualization of the world knowledge that we propose, that should be in neurosymbolic copilot.
I see. Okay, very good. So we may expect a little bit more on this in a few months. That's great. Okay, very good. Dr. Hanson, do you have more questions for at this point?
No, I think we're good. Thanks.
Very good. Thank you. I'm going to ask you a couple of questions on causality. One is we'll go back to let's try slide 40. So you have these causal agents, and there is something called a causal graph. So now you have a collider, or V structure, or converging connection. All of these are used in causal graph or causal Bayesian networks. And at B, so this is clearly dead. And when you see this, you come from probabilistic reasoning, community. You think induced dependencies. So D and A are possible causes of B. So they are unconditionally independent, but upon observation of the effect B, they become dependent because one can explain the other away, for example. Does you incorporate that kind of reasoning in your system, or you avoid intercausal reasoning? So, for example, that's a way of representing something close to the single fault assumption. So if you have multiple causes and you establish one, your belief in the other causes being there, is decreases. Okay, that happens in Bayesian networks. Do you ever have a use for that in your system? Maybe not. That's possible.
Yeah, you meant direct and indirect causal effects?
No, I don't think just that. I think induced dependencies. So dependencies that you cannot read by following just paths, but where you have to actually look at these converging arrows onto a node. And so you may think that, so in the case of DBA, if D and A are both causes of B, typically that means that D and A are unconditionally independent. Okay, there is no reason why one should be affected by the other but in you, unless you model that explicitly with additional links, but upon observation of the common effect, they become dependent. And that's very powerful kind of reasoning if you have a causal model. So that is one thing that I would suggest. Maybe if you haven't incorporated this or thought about it, maybe you think about it, and see, hey, did I ever run into a situation where something like that would be useful? We do it all the time in diagnosis, right? When you see a fault and you say, okay, this fault may be due to this or this. I establish this, but not the other. Okay, and then I say, okay, I'm not going to look at the other anymore because I have a good enough explanation of the fault. Yeah. So that's a kind of intercausal reason. So just a suggestion for possible future work if this is not already caught here. So also on causality, let me ask you another little thing if I can find it. Yes, you got. Let's go to slide 56. So on the right, you have, and you mentioned this when discussing this talk. You mentioned counterfactual, directionally testable counterfactual. Yes. So I'm not asking you to define directionally testable, but could you give me an example of counterfactual in the domains you've looked at in this industry 4.0 applications?
Yeah. So in the smart pilot system, which we have developed, so there, like we want to see how the change of one sensor variable affects the other variable causally. So in there, like we had given like here user can change the cause variable and the effect variable, and he can see the distribution of the for example in potentiometer 1, and then he can set the intervene value to some value and see how it affects the other variable causally. So we have developed an algorithm for this, which includes the causal graph, which was developed by the causal trace agent, and it takes the causal strength and then intervene the counterfactual effect of this intervention. So that is one way we have tried to analyze this counterfactual effect. And
so in most discussions of counterfactual reasoning, there is another side to things that isn't caught here. And this again is something that where I would like you possibly to explore the issue, and you don't need to do anything. It may not be important for this kind of application. But the idea of counterfactuals is that you you do a kind of what if analysis. So you're saying something happened, you know, uh, my production line met certain performance parameters, you know, with the input I gave it, with the settings I provided to the various stations in the line, or something like that, or with the quality of the raw product I gave it. Okay, and now I want to find out what would happen if I had a different quality of one of the input components or input raw materials. Would the resulting product I get be still meet my performance parameters? Okay, and could I sell it still? That kind of thing. So this is counterfactual because you don't have that different kind of raw material. So you're saying, what if I did that? The only way to be absolutely certain of that is experiment. So I'm going to try another raw material. But if you have a causal model, you know, in some cases, in many cases, in fact, you can do reason counterfactually and say, okay, all the variables that I need to do my analysis, I can establish based on what I observe, okay? And then I can do the change in this, in that one variable, because the other ones are fixed, okay? Since you have this stable causal model, you have fixed a lot of variables by the case you have, and then only one variable, the composition of a raw material, is modified. There is no reason to assume anything else changes other than through the causal links, because you believe in the causal model. Okay, so this is the kind of counterfactual reasoning that you should also look into a little bit. And I can suggest a reference or two on that particular counterfactual reasoning, which I think is really the most interesting.
Also, Dr. So in this work, we kind of do like similar to that thing. So it can answer like questions like, so if I maintain this machine 300 hours earlier, would I have been able to mitigate this?
That's a nice
questions can be like, yes. We have these types of questions in this project.
That's a nice example. Thank you. Very good. Thank you.
I have one question, Chathurangi. So can you clarify a bit about your definition of embodied QA? Because from what I know, in the embodied QA, it's a task that was like famously introduced some time back in the robotics community. So you have an autonomous agent, autonomous robot. Basically, if you have like a general question, about an artifact that is not clearly visible, so that requires the robot to navigate in the environment and seek answers. So I'm trying to understand what is your definition of embodied question answering in this context, because I don't see any navigation that the autonomous agent has to do to seek answers. So as opposed to general, visual question answering or just Q&A setup, what is embodied here? What is the definition of the embodied QA in this context?
Yeah, that's a good question. So by embodied, like most of the early work, they, as you mentioned, they are confined to this vision and basically how we deal with images and how really the robots work in a real environment and how they capture signals and how they see images. But there was no work in past that did this using time series data. So that was one limitation that we identified. And so for that, so this what is happening in this embodied loop is it perceive, reason, predict, and then decide on something. So we wanted to incorporate that in time series data. So how can we model the perception in time series data? So that is again based on time series question answering. So what we meant is that using time series data, how can we derive some questions related to perception? For example, identifying like simple questions like, is there an anomaly at this timestamp when the mean is this one, variance is this one? So that was one type of question related to perception. And then reasoning, like reasoning question, like for example, like some diagnostic question related to that. So what type of anomaly happens in this, or like temporal questions, like how many anomalies happen between this time window that we are considering. So so to answer like this kind of questions, we really want to go to the exact time windows and the grounding of the time concept. So that is what we actually meant by embodied here. And also so the answers, they are grounded in the real world sensor data, means that it contains the time window, what sensors involved, and what are the deviating patterns, and what features includes. So what are the provenance details For example, like at what exact time, location, the answer was obtained. So this kind of thing. So by that thing, it differs from the standard embodied thing which is available and which you are referring to.
Yeah, I think so. One comment from my side is like, a little bit careful on the definition, because there are a lot of published work on the embodied QA, and I don't see that embodiment, the embodied part in your definition, because to me it looks like knowledge grounded time series question answering is what is happening here. So the fact that you have the answers grounded in knowledge doesn't, in my view, doesn't make it embodied. So when you submit a paper, probably the reviewers may raise this question, because there's a lot of literature from the robotics background on the embodied QA that almost always include autonomous robot navigating in the environment and seeking answers. So it requires all the loop from the perception to comprehension to planning, and in some cases, knowledge grounding. Yeah, you may want to look it up. Yeah. Thanks.